rejoin you back as promised with some quantum work. A little later than anticipated. Took a little break, relaxer. Of course, we've been doing a lot of studying recently. Went to my quantum professor's office hours. Went to my thermal professor's office hours, which is what I guess technically that was a review day. So, and by the way, I noticed that the video yesterday it had a sort of um, something sounded off about the audio. So let me know if I sound okay right now. I'll pull up the vid myself, but I'm not sure if it always shows properly for me. I'll try to take a look and see if I can hear myself without y'all hearing me at the same time. But it still sounds gravelly, I guess. I think I have to turn down the gain some. Testing 1, 2. Testing 1, 2. Testing 1, 2. Testing 1, 2. I think that sounds a little bit better with the gain down a bit. But let me know what y'all think. Because I don't know, I'm not aware of changing anything. So and I'll try one more thing. Turn my gain down on my mic. Turn it up on the stream. So that sounds a little bit less gravelly. So let me know what y'all think. And I'll go ahead and get on with the stream. So as promised, I'll be doing some quantum problems today. Uh, Reminded me of how much I forgot, basically, of the quantum that we did. So I have to remind myself a bit. Let me know if you have any questions along the way, and we'll go ahead and get started. When I forgot I'm using my horizontal pad, now I'll give you all the bigger screen view. So what we're doing today is perturbation theory. So, and I'll talk a bit about what that means. For quantum 2, perturbation theory. So the way it works is if we have a quantum particle or a small particle, and in quantum 1, we basically calculated the wave function for that particle. So psi basically lets us know that the properties of this particle. So for instance, this might be the wave function dealing with a particle in the box. This would be the wave function for the ground state. This will be the wave function for uh, the first excited state. Here is the second excited state. You can see how each one has another loop around. And so the idea is that that's like the basic particles in the box, uh, one-dimensional well. So the idea is we can actually take this particle box and we can perturb the well, for instance. We can perturb the well and put, let's say, some energy at that spot. So that energy could be, in reality, for instance, another particle or something, like something that increases or lowers the energy here. So now we know that the default ground state looks like this. And obviously we know that this lifting of energy will adjust the wave function over there. So, what will the new wave function be? What would it look like? So perturbation theory basically alters the conditions or the environment of the particle a bit, and making that alteration, we take and see what, make one adjustment here, we take and see what the new wave function will be like. There we go. So what we'll do is we'll look at a few problems like this and some of the theory behind it. So one problem, which would be basically the example that I have here, let's say that we have a particle in a square well, and it's in an infinite square well. We'll call this 0. We'll call this a over 2. And we'll call this a to define the length of the well to be a. And we're saying we perturb the well with potential VO. So here it's 0. So the well is infinite here. So this is V. It's infinite here on this side. And here it's 0. And there the potential is VO. So that's a perturbation, a small change in the well from the default state. So it's saying use the perturbation theory to calculate the first order energy correction to the lowest 5 states. So the way it works here is we take the default uh, equation and we just make some adjustments on that. So if I had a particle, just a regular particle, no perturbation, you can guess that psi x is a sine kx plus b cosine kx. And going back to this scenario, so this is the scenario that we're doing here, and I'll make it a different color to illustrate that. We're doing this scenario here in blue. So I'll make this in blue. So we know that in this blue scenario, the function at 0 is 0, and the function at a is 0. So those are what's called boundary conditions, the boundaries of the scenario. And we use that to help determine what the wave function has to be, because we're going to have to match those boundary conditions. So we can say psi of 0 equals 0, which is going to be a sine 0 plus b cosine 0. And we know cosine of 0 is 1, so we can't use that. Sine of 0 is 0. So we know that sine of x for the left side can be a sine kx, eliminating the cosine. And then for the right side, sine of a equals 0. So it's going to be a sine ka. So if I divide by a, that'll give me 0 equals sine ka. And if I take the inverse sine of each of these, that'll be sine inverse 0 equals ka. And anything that is an even pi, so we do with radians when we use in angles in physics. So we know that n pi is going to be 0. Give a sign that's 0. So we can say that so we can say that K equals n pi over A. So that means that the default equation for the particle in the well is going to be a sine of n pi over A times x. And K is the adjustment to the x value. Now we have to figure out what this A value is. And the way it works here is if I'm going to have a particle in the box, if it's in the box, there's a 100% probability that the particle is in the box if I put it in the box. So that means that if I integrate the probability distribution function, which is psi squared, if I integrate this over all of infinity, which in this case is to integrate it from 0 to a since the box goes from 0 to a, is going to have to equal 1. So this probability distribution, which is the psi function squared, it gives us the probability of the particle being wherever we put these bounds at. So since the bounds are over the whole box, we know that it's 100% probability. So I could just solve that for 1 and find out what A is. So we can say 1 equals integral psi x squared dx 0 to a. So that's going to be, I should say, infinity to negative infinity. So it's going to be 0 to a of a sine n pi x over a squared dx. So that's going to be a squared 0 to a sine squared n pi x over a dx. So that's going to equal a squared 0 to a, and you'll also use the trigonometric identity for that sine, the double angle formula. That's going to be 1 minus cosine 2 n pi x over a over 2 dx. So this is going to give me, if I take the integral, a squared x over 2 minus sine 2 n pi x over a. And this is 2, the derivative of the top. That's going to give me a at the top and 2 n pi at the bottom. And this is from 0 to a. So we have a squared, a over 2 minus, and when I put the a in for x, a sine, and I put in the a for x, that's really just going to leave 2 n pi over 4 n pi minus, and we're going to have 0 for everything there, so that's going to be minus 0. And as we discussed earlier, n pi is 0 for sine, so 2n pi is just a multiple of that. Doesn't matter how many, you can just absorb that into the n. So this is 0 as well, and it all equals 1. So a squared equals 2 over a. So that means that a equals square root of 2 over a. So that means that the psi function for the default particle in the box is going to be square root of 2 over a sine n pi x over a. So I have our default equation that we're going to end up perturbing the well with to get the energy for. So the way the perturbation works is, I need to check my notes for this one. If I was to solve this equation normally, we would have some Hamiltonian for the let's say we have some Hamiltonian times the default wave function with some n, which is that function there. So basically this is sine 0 right here, and we multiply it by Hamiltonian, we'll get some energy and the original function back. So this becomes the Hamiltonian. That's the default wave function which we solve for. And this is the eigenvalue. And since this equation works the Hamiltonian, it makes it the eigenfunction. So in linear algebra, if you have a vector and you multiply it by a value, a function, and you get the same vector back scaled, like with a scalar on it, and that makes the whatever you're multiplying it with, or just physics terms of Hamiltonian, but it makes the value that you get on the other side the eigenvalue, and the function on both sides the eigenfunction. So what we need to do now is we need to perturb, or get the perturbation for the new h. So the way that'll work is h prime, which we'll call the, I'll just call it h according to the textbook. The new h, the new Hamiltonian, is going to be the original Hamiltonian plus something to perturb it with. And we'll put a lambda there to signify that this is a uh, first order perturbation of the Hamiltonian. So the idea is that with this new Hamiltonian, if I take h, I assign in whatever this new side is going to be, it should give us the new energy and psi n. So this is the corrected Hamiltonian, and we're going to need some kind of a different function to work with this new Hamiltonian. It's going to give us a different energy value. So basically we need to get a new eigenvalue and a new eigenfunction for this new Hamiltonian. So the way this works is we load our h there. The new psi is going to be, we're going to start with the original psi, and then we're going to perturb it. Here's going to be the first order perturbation. This is going to be the second order perturbation, and so forth. So perhaps I should put the 2 up. The idea is that we need to find out what uh, the new psi is here, and the new energy that we will get will still be based upon the original energy that we had before, plus some perturbations to the original energy. So this will be the first order correction. This will be the second order correction, and so on and so forth. So all we have to do to find out what this new energy is going to be is plug these in into the new equation that we have here. So the equation that we have here for the perturbed Hamiltonian, the perturbed, and the perturbed Hamiltonian will be the basically what we have with the new potential value. We're going to have the new energy going to do psi. So this will end up being, oh, and I can actually, this is the current problem. Put all of this back in black. So I'm going to plug this into my equation 1 here. And we're only going to the second order. So we can say H naught plus lambda H prime times psi plus lambda psi in 1, since we're only going to the first order, equals, and only up to the first order of the energy. We have to repeat psi again because whatever values we get for everything, they're going to still keep the same um, relationship of being eigenvalues and eigenfunctions. And that was correct so far. So what we need to do here is go ahead and distribute each of these things. And what this lambda does is basically is a placeholder for how many orders we're dealing with. So we would have H naught psi n naught plus H naught lambda psi n1 plus lambda H prime psi n naught plus lambda squared psi n1. And that's going to equal this. Actually, let me just write the whole thing and make this word lambda psi n1 squared. Me this up a bit. To the other side. Yeah, that got mixed. Okay, we're good. So we had E naught n psi n naught plus E naught lambda psi n1 plus lambda E n1 psi n naught plus lambda psi n1 squared. So I only want first order. So since that's going to be lambda squared, I can actually cancel those out. And everything else seems to be first order, except for actually this is our default. So we don't actually need the default one. I mean, that's true, but basically this is the original Hamiltonian and energy that we have already, that we know already. So we can simplify this to be H naught lambda n1 plus H prime lambda n0 equals E n naught psi n1 plus E n1 psi n0. Now, the key technique to simplify it from this point is to integrate everything on both sides by the same thing. And what we're going to integrate everything with is the psi n naught uh, complex conjugate, which is psi n naught with a bra. So I'll go ahead and do that. Now we have psi n naught, h naught, psi n1 plus psi n naught, h prime, psi n naught, and that's going to equal psi n naught, e n naught, psi n1 plus psi n naught, e n1, psi n naught. So looking at this, that this is just a value, so we can actually pull this out. And after we pull that out, the side functions are orthogonal, meaning that if they have two different values with the nothing in between them, they're always going to equal zero. So these wave functions are basically behave like vectors as well, because we use linear algebra and eigenvalues and eigenfunctions. As I said before, just like a vector. So these wave functions behave like vectors, how you can combine them. So they're orthogonal, meaning that their in values are different, or their characteristics are different, not equal, then equal zero. Um, this one, I believe, should stay. And let's see what else cancels out. The default Hamiltonian is Hermitian. So since the default Hamiltonian is Hermitian, you can actually pull this out. Put it on either one that we want. So we can do this like this. And for the same token, these are different. So this is going to equal zero. And what will remain, which is what we're looking for, the first order corrections of the energies, what this problem is talking about. Um, energy is still just a constant, just a value. So whenever you have just a value, you can pull the value out and put these together. So here we had 2n wave functions, but their order was different, so they equal zero. If you have two similar wave functions with the same order, they equal one. So that means that we have en1 equals this. So now we solve for the energy as the correction for the perturbation of the first order. So energy will be, as we said earlier, E naught plus En1. And this will be the total corrected energy for the perturbation for the first order. So the first order energy is going to be what it is. N squared, pi squared, a bar squared over 2ma squared for the infinite square well. So now we're going to calculate what En1 is. And we already know psi n naught. It's going to be square root of 2 over a sine in pi x over 8, which we solved for earlier. Here. So we can go ahead and work this out. The new Hamiltonian is basically we could put in V naught in its place. And what's the best way to explain that part? We got an explanation for the Hamiltonian and why it's V. The textbook. See what I can break down for that. And let me know if you have any questions in the meantime on what we covered so far. And I'll get this detail for you. So what we're doing is you can actually consider the uh, perturbation in terms of the fact that that's different from the original Hamiltonian is what I'm understanding here. So if they tell us that the perturbation is V naught, so remember our particle in the box was perturbed by V naught here. So if it tells us that the perturbation is that is our H prime. So you end up with the full Hamiltonian, which would be here, plus just the whatever the perturbation is our H prime. So it's not necessarily a full Hamiltonian, but it's the change in parameters that's actually acting on the wave function given a perturbation. So when I actually take this integral, I can say E and 1 equals psi m naught H prime, which is the perturbation itself, m naught. So that's going to be the integral. If I was to do so one thing to keep in mind is the perturbation is only on half of the well. So the first half of the well, the perturbation is 0. There's no perturbation now, so we could ignore it there. So that means that since we're integrating only for this perturbation, which is V naught, we can only use the bounds for that V naught. So it's going to be integral A over 2 to A, square root of 2 over A sine n pi x over A. That's the first wave function. H prime is V naught. And then we put the wave function there again for the proper calculation of the integral dx. So this is basically formalism, basically quantum mechanics notation for this integral here. Now I can just solve this integral, and which I solved before. So I'll be brief with this since I have no onlookers at the moment. When we actually solve this integral out, similar to the process we did before, we end up with V naught times the integral, and it ends up being V naught times 1/2. We take this integral. So that equals E naught 1. So E naught 1 equals V naught over 2. So this means that when we have this particle in the box for size of V naught on the right half of the box, the energy of all the states increase by 1/2. So just add 1/2 to whatever's going on, and that makes sense. So if we look at this, the initial state, we boost it up. So now it ends V naught higher, so that's boosted, but it's only on 1/2 is boosted up. The second state, even though the wave function is 0, it'll be V naught for free right here, only 1/2 of it. And the third state, similarly, half of it has to be not pushing it up, so it's pretty straightforward. Another thing we can do is we can solve for the wave function correction, but it's a bit more complicated. So we can say what will be the corrected wave function for psi given the new energies that it's dealing with. What's the new wave function? So here's derivation as well. We can go back to here. Which is this part here, part here. So I'll call this equation 2. So we can go back to right when we distribute the uh, values for the new Hamiltonian expansion, the new energy expansion, the new psi expansion. We substitute that into the new linear algebra expression. We can go back to that form, but instead we're going to solve for psi. Here is, because now I want psi, I have the energy. Here is the energy correction. It's 3. So I'm going to solve for the corrected psi. Say that H naught psi n1 minus E n naught psi n1 equals E n1 psi n0 minus H prime psi n0. Then I can, what we're going to do next is we're going to have a key step. So a key step here is to recognize that, as we said before, these uh, wave functions are basically like vectors. And you can have a vector like this, and it can be made up of any number of smaller vectors added together that equals up to that same vector. So by the same token, the corrected wave function that we're looking for, the first order correction, can be made up of any number of the original wave function with a proper coefficient in front. So these wave functions are going to be different energy levels than the original wave function. But basically the idea is that because these are basically vectors, we can take some number of wave functions of different energies and add them together and get the same energy. It's like how we can take 1, -2, and get -1. You can also get -3, 2, and get -1. There's many ways to get -1. You just have to add other numbers in a proper way. So by the same token, we can add other numbers in various ways to get -1. We can add other functions in order to get the correction function. So what I'm going to do is I'm going to substitute that for psi n1, since I know psi n1 can be a combination of other functions. I'm going to put in this other function, so it's just like how other numbers add up to -1, other functions, so that's why it's going to be m equals not m. I'm going to use sub m for the other functions. So what we can do here is look at how this will play out. Make sure that I take the proper step. What we have here is we have a default Hamiltonian on a default wave function with m. So that's actually going to give us an energy with m and the same wave function back, just like how we talked about earlier. Here, what it just states what it is. That's just an energy. And on the other side, you can actually just factor that a bit. Now, what we could do here, since we have the energies worked out, we can actually do some more factoring, and you can put the summation in the front, have that, and everything is looking good so far. Uh, Another thing I can do here, since I have it in this form, is do a similar trick as before. So this one actually has two tricks. One is the recognition that side N1 is some multiple default wave functions. And also we can actually do like we did here, and we can multiply by default wave function of a different entity, which is going to be with that additional wave function. Check my screen. It seems to be saying that there's an issue. Like two are watching. I don't know why it's saying the stream is stopped. So feel free to drop a line. Seems fine. All right, so I'll keep it going. Feel free to drop a line those who are watching. So let's show the first trick for getting the uh, perturbed wave function. We identified that the perturbed wave function would be a sum of default wave functions. It was going on, Catherine. Oh, all good. Okay, thanks for popping in. So I'm just solving for a perturbed wave function and some difficult stuff. Perturbing a square well, a lot of steps. The exam is supposed to be mostly conceptual, so you have to make sure to understand the concepts. Is the stream looking okay, by the way? I don't know what's up with this. I think I fixed the audio. The audio did sound a bit scratchy yesterday or something. I had to turn the gain down. Even though I remember changing the gain before, but it is what it is, I guess. And I think it sounds okay now. Right now, the software is saying it's not streaming, but it is. So, let me know if there's any issues with anything. So I'll go ahead and do this multiplication. I'll make sure my notes up. So I'll multiply a different energy. Right? So we have that multiplied, and then we want to multiply this side with the new wave function to eliminate some things and make this easier to work with. So once I do this, I can actually distribute everything a bit. So this side is just an energy. So that's just going to come out in front. Awesome. Thanks for letting me know, Catherine. So we have M equals not N, E M naught minus E N naught. And we shall do Cm N, since that's a coefficient, psi L naught, psi M naught. And on this side, we have to distribute this to both of these. So this side will distribute to both of these here. We have psi L naught E M1, psi M naught minus psi L naught H prime, psi M naught. So this is just an energy. So I should be able to take this out. En1 psi L naught psi N naught minus, so this is going to have to stay because that's a perturbed Hamiltonian. So we should need to take the integral of that. And this is going to be 0. Let me make sure, did I miss a step? I'm jumping the gun a little bit. So that does jump out. This does stay the same. Right? And what happens after this determines on if N, L, and M are they the same or different. And right now, the operative factor, the bra that we uh, multiplied in, the bra that we multiplied in with the kets to do the differentiation will vary that. So we can say if L equals N, so M is basically the second level one that we're working with. N is the one that we actually want the perturbation for. So we'll actually work with N. And let's see what happens if L equals N. So if L equals N, this means that this would be sum M equals not M, E M naught minus E. So L equals N. So where I see an L, N, I'm going to put an L, C M N, psi L naught. And actually, I'll do the reverse. So where I see an L, I'll put a, instead of a word, I see an N putting an L, I'll put a N. Since eventually we'll get back to N. So I saw one L there, I put an N, and this will be EN1, N, N minus N. There's already an N. All right. So now we can actually do the cancellation. So we have to, even though it's all right to pull this out, but now we can cancel after we know what is what. So this is the perturbing Hamiltonian, like in the current problem, this is V naught. So whatever the perturbation is on the state, that in itself is the Hamiltonian prime. So that will stay there. This is the same energy wave function times itself. So this is always going to equal 1 due to orthogonality. And this is going to equal 0 because these are wave functions of different energies. So that means that we have 0 equals En, so the 1 minus the expectation value of the perturbation. So if we see that if L equals N, we just get the energy of the perturbation, which we saw for before. So I always thought that this was interesting, that this is another way to solve for the energy that's perturbing, the energy, the new energy of the wave function, or at least I should say the correction to the energy of the wave function given a perturbation. Sometimes I wonder why they don't just teach this way only as the way to get the energy. They teach the first way, I did it first. And they only teach this way to get the wave function, but it just so happens that when we add this bracket into the situation, uh, and the bracket is such that when L equals N, we actually solve for it too. They're just trying to treat this as an aside. So it seems like it's possible just to just solve for psi and then put L equals N and L equals not N. L equals N gives you the energy, and L equals not N gives us the wave function. So if L does not equal N, the idea is that we know that M can't equal N. That's here. So if L is not N, L should be M, just the understanding. L can't be N, but it could be M. M can't be N, and N can't be M, but L could be M. So we'll choose to let L equal M when it is not N. So now I go where I see an L, I want to put a M. So we have some, so I miss a step. I think that's good. Right. M equals not N. And I'm going back to here to plug stuff in actually here. So we have EM naught minus EN naught CM N. So now this is going to be M naught psi M naught equals EN1 psi M naught psi N minus psi M naught psi N. All right. So looking at this should be 0 since they have different energies. And this should remain since there's a perturbation in between there. So we don't know what this is going to do to the wave function. And these have the same energy. So these are going to equal 1. You can say that all of this equals this. Factor in the ones and the zeros. Now we need to solve for, so we have to go back earlier. Earlier we declared and understood that whatever this perturbed wave function is, it can be made from a sum of the default wave function, which we know already. We solved for it up there. we need to know what this coefficient is to give us the proper amount of the default wave function so that when we add them together, we get the perturbed wave function. So I need to solve for Cm here so I can know what to do with that. So this is going to be psi m naught h prime psi n naught over, and I'm going to take this negative sign and multiply it into the energy. So we have E n naught minus E m naught to get rid of the negative by simply multiplying it in and swapping the signs of those. So what this means is that plugging will be found into here. Now we know that the wave function, the new wave function given the perturbed uh, well is going to be a summation m equals 9n. So again, just like how we multiply or add various numbers together to get -1 that's different from -1, we're going to add a bunch of wave functions that's different than the one that we have. And we're going to say this is psi m naught h prime psi n naught, plugging in for what c is, divided by e n naught minus e m naught, and then the wave function is already there. So this becomes the wave function for the perturbed well. And let me see if I'm going to number this this equation here. So this should be 4. So let's say I wanted to get the, okay, thanks for letting me know. So yeah, I don't know what changed about this. About now. Currently I need to do this. Let me see. What about now? Is this, hold up. Is this better? I'll go back to my default mic, see if that helps. Awesome. Right. So try to get too fancy on the sound there. So let me, I'll rename this. Awesome. So I'll keep it like this going forward. Thank you for the feedback. So yes, try to keep the audio nice. All right. So we have this. So why don't we go ahead and calculate the perturbed wave function for uh for this for this perturbation that we have. So let's say we wanted the perturbation for the first order perturbation uh for the zeroth energy state. So let's say I want this, the perturbation for the ground state. Basically, we can just add up some wave functions. So we can go psi 1 with the perturbation over plus, oh, I got to put the wave function at the end. So we want the ground state. So this will be 1 plus, and I'll just go 2 in psi 2. So this is, so basically m just can't equal n. So n equals 0. So we have m equals 1. M equals 2. And we could keep going. We will stop here and see what values we get for this. So if I was to calculate this first one, that's going to be the integral. And I actually don't remember if we calculate this over the entire wave function or over the entire, what do you call it? Well, or just the first half. So let me take a look and see what I did last time and confirm if we integrate over the entire well or just the part that we have the perturbation on. So psi, all right, here we go. So it looks like it's just the part with the perturbation. So, which makes sense because perturbation is only there. So this would be a over 2 to a. This is going to be square root of a over 2 sine. So here n is 1. So this is 1 I x over a v naught square root. Did I invert that? 2 over a sine, and oh crap, well that one would be 0. So we're taking the base wave function. Looks like there's no change in the wave function for that one. All right. So we have to go higher up. So basically the base wave function is the same, which ironically matches what we had. If we scroll back up, the default wave function was the same, and we showed that. So everything is actually adding up nicely for what it should be. So why don't we do the first order perturbation for n equals 1. And I'll copy this over and change the numbers a bit. So here, n equals 1. So m equals 2. And m equals 3. All right, so let's see how this looks with this one. This is a 2. All right. So I'll copy this. So now we have, I'm doing the first one here, here. So we have side 2, and I'm gonna confirm, and that should be 1. So n equals 1. I'll put n equals 1 here. That's the one that we get any correction for. 1. So this means that we have 2 pi x over a v naught, 2 over a sine pi x over a dx. So this looks like one that we can solve. Looks like it's not automatically 0. So we have a over 2 to a, 2 over a, and sine, we could say 2 v naught over a, sine 2 pi x over a. Can you do it to the nth degree? Yes, you can. So the idea is that you can solve this as far as you like, but it's just the higher degrees you go, the smaller the value is. So it becomes um, you're not worth it the farther you go, is my understanding. So it's kind of like the first part will be that big, and the next part will be that big. So basically, the main wave function is like that. We perturb it just a little bit. You have to correct it a little bit and a little bit, and each one it gets smaller and smaller, and it becomes to the point that we don't have to worry about it anymore. Similar to the approximations that we do in thermodynamics. Eventually, the approximations down here are no different than the statistical variations. And we were talking about how when something is in the highest probability, the highest entropy state, there is still some fluctuations from that state left to right. It doesn't like break the universe, it's just there's some fluctuations. So eventually the errors become smaller than the fluctuations, or it's just hitting up in there and it doesn't matter. And Catherine says, wouldn't it be a 2 at the very right? Let me see here. No. Oh, no, no. So what we're doing is we're doing just this. So just that part right there is this. Just that one part. And then we'll have to do the rest. I mean, I'm sure it's possible to do it all at once, but I'll try to break it up. So just that part, n equals 1, m equals 2, n equals 1, m equals 3. And m2s, m2s, and yeah, that looks right. So I got into the habit of breaking these into smaller chunks, just like I coach my students to do as well, because it helps. The second one I have in mark, you're talking about this one here. So basically, let me make sure I understand your question properly. So like this whole thing here, this is that, this is this, and this is this. And you're saying I missed marking something else? I may have missed something. So this, I'll add this in later. And this, I'll add this in later too. So I believe I did that part right. So the n is 2 for this one, the first one, n is 1 for the second one, and we just take the integral from there. Yes, that's right. That's correct spelling, psi. The psi on the right, for that one, n equals 1. So basically, I have a 1 here for psi of 1. So the one on the left is 2 for n. The one on the right is 1 for n. The yellow one is 2 for n. The green one is 1 for n. V naught is just what it is, and I believe that's right. So the sub value is the n value, and we're using the default wave function of different energies to add up to make the perturbed wave function. And I should remember how to do this integral. I can think about it for a moment and see. Or else I might just plug it into a calculator. We shouldn't have to do anything like this on the exam day. Thinking about it, this should be 0. Because no, actually the bounds are different, so it may not be 0. All right, let me put this in the calculator and see. I remember how to do this integral. Either it equals 0 and I don't remember it, or there's some integral trick that I can't recall. Oh, that's interesting. I don't know why that happens sometimes. Like sometimes you can see my mouse and sometimes you can't. For this integral here, I don't remember how to do that integral. I don't believe we'll have to do it on the exam. Let me put it into a calculator and see what I get. So I have a over 2 a sine of 2 pi x over a sine pi x over a dx. All right, let's see if we get a 0 or what we get. Oh, we do get something. Crap. Oh my gosh. So integration by parts? No. Let's see. All right, I'll figure out how to do this integral and I'll show y'all. It'd be just my luck that an integral like this is on the exam. All right, so we have to use a trigonometric identity. I hate those. All right, so it looks like if you have sine A and sine B, that's the same thing as 1/2 cosine A minus B minus cosine A plus B. All right, so if you get an integral, because of the bounds, you're not sure if it's 0 or not. Like if this was over infinite bounds or symmetric bounds, It should be 0 since the sine values are different. And I could test that out as well. I can plug that into the calculator and see. Like if I was to integrate this from uh, -a to a, for instance, comes up 0. Because if it's symmetric, or you have signs of different energies, it's going to be 0. If the bounds are not symmetric, like if you have a perturbation, then you have to use this identity. So let's actually see how this goes. So this equals 2v naught over a integral a over 2 to a. So this is going to be 1/2. So I'm going to have another 2 here. Cosine of 2 pi x over a minus pi x over a minus cosine of 2 pi x over a plus pi x over a. I'm not sure if this helps. So I believe they're still different. Oh, well now I have two integrals. That's what it is. So what ends up happening is I have equals v naught over a integral a over 2 a of cosine pi x over a dx minus integral a over 2 a v naught over a cosine 3 pi x over a dx. Okay. So the trigonometric identity makes us have to do two integrals, but we can actually do the integrals. All right, so let's see what this is. We have v naught over a. Oh, hold up. Actually doing the integral. V naught over a uh, sine pi x over a and dividing by an integral. So that's a over pi and x equals a over 2 minus v naught over a sine 3 pi x over a divided by the integral of derivative a over 3 pi, and that's going to be also a. All right. So looking at this, we have v naught over a. So we have a over pi sine pi minus a over pi sine pi over 2 minus, so the v naught over a I'll put in the front, a over 3 pi sine 3 pi plus, because it's going to be minus a minus, a over 3 pi sine 3 pi over 2. All right. So sine of pi is 0 and sine of 3 pi is 0. And sine of pi over 2 is 1. and sine of 3 pi over 2 is -1. So we have V naught over A times minus A over pi plus A over 3 pi. So that equals V naught, and this is going to be 1 over 3 pi minus 3 over 3 pi. So this is going to be V naught, negative V naught, negative 2 V naught over 3 pi, if I did that right. Let me see. Oh crap, I made a mistaken. I deleted the answer the calculator gave me. Let me put it back the way it was. And that looks right. All right. So that's how you do that integral. Let me just put it in a better form. We have negative 2/3 V naught over 5. And all right. So that means that this is going to go on the top there. So again, we're still plugging in for this. So all of that was still just the top part of this solution to the, and perhaps I'm just going to do the first one actually. I'm going to do the first one. We're going to just make this approximation. No. So, oh, crap. All right. So just for the top, this equals negative 2/3 V naught over pi divided by E1 naught minus E2 naught psi 2 naught. All right. So the energy of a particle in the well, the default energy with the zero at the top, is going to be m squared pi squared h bar squared over 2m a squared. So E1 equals pi squared h bar squared over 2m a squared, and E2 naught is going to be 4 pi squared h bar squared over 2m a squared. So E1 naught minus E2 naught is going to be 3 pi squared h bar squared over 2m a squared for the energy. And we already know our psi in naught is square root of 2 over a sine n pi x over a. So psi 2 naught is square root of 2 over a sine 2 pi x over a. So now we can put all of this together. And we can say that the first order correction using just one calculation for an approximation is going to be negative 2/3 V naught over pi divided by 3 pi squared h bar squared over 2ma squared. And we're going to multiply this whole thing by the default wave function with n equals 2. All right. So this is one way to write the wave function perturbed by putting a half of the well with a potential perturbation of V naught. So we're going to have corrected the full psi is going to be psi n naught plus psi n1. So there's going to be square root of 2 over a sine n pi x over a. Oh, well, I made n equals 1 pi x over a plus all of this. So this is basically how we would need to write the new psi for the new wave function for the perturbed well. And the energy, the energy would be E1 naught plus E1 1. That's going to be pi squared h bar squared over 2m a squared plus, what do we get for the correction? It's way up here somewhere. V naught over 2. The bastards. All of that for the function. V naught over 2. All right. So now we have the new wave function for the perturbation, which is built upon our default wave function. And we have the new energy value for the perturbation built upon the new energy value. So let me know if y'all have any questions about that or any comments about that. Getting the new energy and the new wave function for a perturbed well. I'll get a drink of water while you think about it. Man, so it's been an hour and a half already. As you can see, perturbation theory is complex. But let's review what we did so far. I may call it here. So basically, we solved for the default wave function. That's the first problem we did as a preparation for the correction. And Carpenter says, what happens if you do it to the nth degree? It takes a lot of time. And to make sure I'm understanding what you mean, what do you mean right here? If I just keep this going to like y equals a million or whatever? Or do you mean somewhere else? Oh yeah, it should just keep getting smaller. So right now, and this is pretty ugly to calculate, but if we had a value for L, like if we knew that the size of the box was 10 microns, or whatever kind of well you'll put an electron in or whatever, and we actually calculated all the values, uh, each one should be smaller and smaller. So, I mean, it'll just give you smaller values, but it's not going to hurt anything. Kind of like if you solve a problem on the exam and your calculator gives you as the answer 5.257348293. Like, do we write all of this on our homework assignment, or do we just go like 5.26 and call it a day? So it's just a matter of how much precision you need. So if you're actually doing something like, let's say you're calculating the precise energy of an isotope because you want to make a new type of battery. Well, you might need all of these precision because you want to get the most precise value possible to, you know, to output what your battery is going to do. Um, and this thing is where you need that type of detail, So you might need to go way out here, depending on what you're doing. Let me show you something real fast that's dealing with this precise question and what they do this with. So this is something that our professor showed us um, in class. So let me show you all this. So this is the NIST table. So I spoke about how uh, scientists, when they, uh, you know, do whatever, sometimes they need to get very accurate, and they made those tables like we talked about the other day. I know one day I did quantum, and we talked about um the such Gordon tables where I actually got the atomic, showed you how to get the quantum numbers and how to pick out the proper ones, how they combine with the size. And these are examples of the size I was talking about when you get probabilities. So, in notation, it looks like this little bracket thing here. In notation, even though it looks like this little bracket thing I have in yellow, blue, and green, in actuality, it ends up being an actual function you can use, like this sine function, this sine function. But in notation, it looks like a Brian cat. Even though you can do stuff with Brian cats as well, it gets complicated. But there is a point where you literally write only in this. So I guess I can't say it's always a sine function, but it can end up being just a regular sine function. So and I talked about how they put that in tables, like I showed you that Clark Gordon table, where instead of calculating everything over and over again, you could just go to the table and pick it out. Well, what they also do is they, like chemists and stuff, they analyze these atoms and molecules. So right now I put in iron. So you can see how you have the wavelength. So in other words, if you have an iron, uh, an iron 2 atom, and you uh, hit it with a photon, this will tell you the transitions that it'll do in atomic structure, like which electrons will accept and absorb energy, which will release the energy, what wavelength it'll release at, uh, and so on and so forth. So all of these things are calculated and tabulated. And as you can see, like on my exam, like I was saying, I probably would just round this up to 171 or something, or maybe 171.3. But if you're a chemist and you're, trying to make a new medicine or something, you may need all of these things. Or if you're an astronomer and you're looking at a galaxy and you're trying to determine exactly what elements are in the neutron the nebulous cloud you're looking at, this may make a difference. So depending on what you're looking at, there's different degrees of accuracy that you need, but there are people who need the nth degree, and at a certain point, it ends up being a problem with calculation power as well. So right now, I'm just calculating it by hand. That's why I was like, dude, I'm not even gonna try to calculate this other one. I was going to actually do this one too, and just add them all together before I realized take like another hour in the third one. So I just stopped with the first one, right? Uh, it's calculating power, right? So even quantum computers have limits. So it gets to a point to where you want the computer to run for 2 days to get that extra digit of 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 precision, or is this enough for what we need? And Catherine says that's where I was thinking you will need those extra degrees of accuracy. That's fascinating. Thanks. Listen, I'm glad it helps. Glad you appreciate it. Always good to see you, Catherine. And I actually feel more rusty than not on quantum too. So I'm gonna stop here and do some more self study. And what I'll do is I'll likely come back tomorrow for some more thermal, and then come back Friday for some more quantum, and uh, and then Thursday and Saturday is my exam. So bit by bit, I'm just building up my reminding myself of quantum knowledge and preparing for the exam. I'm gonna go see the professor again tomorrow for his second. Is it tomorrow? Yeah, he has another office hours tomorrow. And perhaps what I'll do on Friday is go over what we discussed today and tomorrow in office hours. So I'll have a good handle on that, I guess, by Friday. And I still am going to show y'all the new stuff we covered. I'll do that tomorrow. I'll do some of the older stuff that I'm familiar with, like some engine stuff, and I'll do some of the new stuff, which is Boltzmann factors and partition functions dealing with fermions. It gets complicated. It's awesome, Catherine. Awesome, everybody else. It should be around the same time, 2 hours, an hour or two earlier from now, 2 hours earlier from now, give or take, depending on what's going on with the offers hours and things like that. But I'll be here at some point, about 2 hours earlier from now, give or take. And everybody else who is watching, thank y'all for watching as well. Feel free to drop a line sometime, a question or a comment. Like, subscribe if you haven't. I do offer tutoring on the undergraduate physics, astronomy, and math. And I hope you have a good evening.